Hello everyone, I hope you're doing well. So in today's video, we're going to go through the 2025 VCE Northern Hemisphere Maths Methods Exam 2, the multiple choice section. I hope this video finds you well and helps you with your method studies. So this paper just came out, I think 2 days ago, and yeah, I want to have a try at it. This is my first time trying it. I haven't heard from anyone like if it's easy or hard. I know exam 1 was hard from hearing from everyone. That's what people are saying, but I'm not too sure about exam 2. So again, this multiple choice section, after I finish it, I'm going to give my opinion, if it's hard, if it's easy, so hopefully it's not too bad. And just like always, guys, if you guys want private tutoring in specialist methods, physics, or chemistry, you can always email me for this email. Guys, I'm going to try to go as much detail into how I would approach every question, yeah? Again, this is my first time, but I also want to give you a lot of, knowledge and how I would approach every question. So let's smash through this paper. Okay, question 1. So it just looks like a typical question that you'll get. So this is this says if x minus 1 is a factor of this polynomial where a can be anything except 0, find the value of a. Absolutely beautiful question. This is like one of the most typical questions that you see in the multiple choice section. So let's smash it. So what I always first do is to first define f of x. So I define this function over here, this polynomial, in terms of f of x. So I can write it on my CAS. So f of x is this, is equal to 3x to the power 3 minus 5x squared minus ax. Now, it is important to understand this. This is a factor, yeah? So if this is a factor of this polynomial, it means the root of it, so to find the root is when you solve this factor, equal to 0, x equals y. This is the root, by the way. This is called the root. When I sub f of a, the root, so if I sub in, the root, it should be equal to 0 if it's a factor. If it's not equal to 0, then it's a remainder. So yeah, so this is, for example, they tell us it's a factor, so we know that f of a must be equal to 0. And so imagine basically defining this function f of x in our calculator and solving this for a. Let's do that in our CAS. A really, really beautiful question. So let's go add calculator and let's write f of x is defined as 3 x to the power of 3, so minus 5x squared minus a times x. Yep. So what I'm going to do is f of a equals 0, and I'm going to solve this answer, comma a. Now look at this. We got two solutions. Now remember, it says that a can be anything except 0. So this is not our solution. It's only a equals 2. What an absolute beautiful question. So question 1 is D. That is your answer for that one. So let me put a nice circle into that. So question 1, D. Next question, 2. So it says, suppose that f has a domain of all reals and g has a domain of all reals are functions that basically f dash of x is equal to g dash of x minus 2, and we know that f of 0 equals 1 and g of 0 equals 2, then what is what? Okay, so basically what they're doing for all of these here is they're just solved for g of x. Okay, so how do I do that? Well, looking at this equation over here, yeah? So looking at this equation over here, I'm going to make g dash of x our subject. So, for example, I'm going to bring that negative 2 to the other side. So, it'll become g dash of x is equal to f dash of x plus 2. Yeah? Now, remember what we want? We want to make g of x the subject. As you can see, it's the subject here. So, but it's g dash of x. How do I get rid of that? Basically, it's the derivative. To bring it back to the original function, we integrate it. So, we need to integrate g dash of x. Now, if we're integrating this side, we have to integrate the other side also. So integrate f dash of x plus 2 dx. Beautiful. And now when we integrate g dash of x, it's just going to become g of x is equal to, of course, f dash of x. So when you integrate f dash of x, so the derivative of f of x, it's going to be basically f of x, the original function, plus when you integrate 2, it's 2x. And don't forget, plus c, we can have a constant. And to find that constant, they've actually given us a initial condition. They told us that when x is 0, y equals 2. Yep, so let's write that down. When g of 0 is equal to 2, so the y equals 2. So basically, it'll be 2. So that this will be 2. And when you're subbing all inside here, the x equals 0. So it'll be f of 0. Plus 2 times 0 is just 0, plus c it'll be. And what's f of 0? We know that f of 0 is 1. So we can actually rub this part out and put a 1 there. Easy. So, and that will be what? like, it'll be c equals 1. That's our c value. Beautiful. So going back to the original one equation, this is 1. The c value is 1. And here is our final answer in terms of g of x. So which one looks like that? G of x equals f of x plus 2x plus 1. It looks like 2 is b. Beautiful. Nice question there. Next question. Question 3. If the integral from a to b of f of x is, equal 3 and b to a of this is actually a typical question. I love these types of questions. So how do I approach these questions? Well, first of all, what we want to find is this, this over here. What I'm going to do is I'm going to break it apart. So you know how for integrals you can, so this is a whole statement. What I'm going to do is I can break the integral apart. So I can break the integral for this and this. So let's do that. So I'll integrate it. We can say b to a of 2f of x. You see that? Dx. Plus the integral, so splitting it up basically, 3 dx. Can you see how I split it apart? Makes my life easier. Now, if you have a constant, you can take the constant in front. Take the constant here in front, that too. And you're left out with this beautiful here. This is beautiful, like that. Now, what is like the integral of b to a? So what does this simplify here? The problem is it's actually not the same as that. Can you see? This is going from a to b of f of x. This is b to a. By the way, if you know this, we know that if we swap these terminals, you have to put a negative in front of the integral. So it'll be negative 2. Look, I put negative in front of the integral. Now we're going to swap these around. So it'll be a to b, f of x dx, plus the integral from b to a, 3 dx. Absolutely beautiful. And guess what? Now we know what this whole statement is, this statement here? We know what it is, as from here. It's right over here. F of x, it's equal to 3. So I'm going to put 3 here. Plus, and I can easily integrate that, because the integral of 3 is 3x. So when you integrate that, going from b to a, so that'll be negative 6. Plus, when you sub in a will be 3a, and then it'll be minus, and then you sub in 3b. Beautiful. Okay, so from the answers, you can see that 3 is taken out, so we can take 3 out. So it'll be 3 a minus b minus 2. Which one looks like that? A minus b minus 2. It looks like D. Looks like 3D is our answer there. Yep, so 3a minus b minus 2. Just want to double check if it's correct. Have I made any mistakes? Yep, looks like it's, for that one here, we can say it's 3D. Beautiful. It's not too hard. It's really nice. The first page is really beautiful. Like, these questions are really typical exam style. Question 4. The graph of f of x is shown, okay? And which option shows the graph of f of x, where f is an antiderivative of f? This is a beautiful question. Really typical question. So what I first of all is that there's multiple ways you can approach this question. My way is basically drawing a number line. And this is how I approach these antiderivative ones. So how the antiderivative graph looks like. And I can kind of I use this method here to kind of see, like, not guess, but I don't know what the word is, like, to get the answer, a possible antiderivative. So for example, this is your graph of f of x, and you can see that it passes through 1. So I'm going to put 1 here. That's a very significant thing, that 1. What I like to then look is, at 1, what's below 1? So what's the below 1? It's this part here. Can you see how it's above the, it's above the x-axis, so it's all positive y values. I'm going to put positive here. So on the left-hand side of 1, and by the way, that's negative infinity, that's infinity. So that means, like, going to the left of 1. Can you see how all the y values are positive? Beautiful. What about, in this case, let me draw it, that's nice. What about, so that's positive infinity. Okay, what about going to the right of 1? So, like, right of 1, we can see that now it's below. So it's below the x-axis, so the y values are negative. This is very useful because this tells me the gradient of the graph. So, for example, if I draw this at 1, so at point 1, say 1's here, at point 1, we can see that below 1, so at the values that are below 1 have a positive gradient. So a positive gradient looks like this. Can you see how the graph is increasing? It's a positive gradient. Yep. When it reaches 1, then after 1, it becomes negative. So it's going to look like, it's going to look something like this. It looks like a minimum turning point. So this is a possible way. 1, of course, is your stationary point. So this is a graph that is possible. Which one looks like that? Of course, it's not A. These are you can see. So that's a maximum. Yeah. So these are C. A and C don't look the same. It is absolutely B. It's absolutely B. There it is. That's your answer. B. The other ones are rubbish. That's -1. It's at 1. What we can also do is there's so many ways you can approach this question. Yeah, that's how I like to approach it. I use this kind of method in Spec. It's a really easy way to understand it. Yeah. And for example, we know that if this is your original function, yeah, let's kind of derive it. Like, let's draw the derivative graph and see if it's the same. Well, we know that stationary points will become our x values. So the x value here. We know here that the gradient is rising. It's positive, so it's going to be above the x. It's going to be above the x-axis. Here, the gradient is going down, so it's going to be below, and it's actually the same graph. As you can see, if you're drawing the gradient function, it's basically the same here. So it's B. So question 4, B. All right. Question 5. The scores of a national standardized test are approximately normally distributed with a mean of 120 and a standard deviation of 15. Andrew scored 117.9 and Chloe scored 1.9 standard deviations above their mean. The probability that a randomly selected participant achieved a score between Andrew and Chloe is closest to 1. So what I like to do here is, of course, draw a diagram to represent this, because there's a lot of information here. Okay, so let's draw this nice normal diagram here. And just call this X, where X is their scores. So we know that the mean is 120, so this mean is 120 here. That's your mean. And we know the standard deviation is 15, but it says Andrew scored 117.9, so which is below somewhere here. This is your Andrew. 117.9, so that's your Andrew. Okay, let me draw this nicely. That's your Andrew. And Chloe scored 1.2 standard deviations above the mean. So basically, 1.2, so it'll be 1.2 times the standard deviation, so 15. So she scored 1.2 times the standard deviation above the mean. So what's 1.2 times 15 first? Let's go on our calculator. 1.2 times 15. It's 18. So let's write that down. So 18. So she basically, she said Chloe scored 1.2, so it's basically 18 above the mean. So if your mean is 120, you plus 18, that's going to be, let's say here, which is 138 in this case. And this is it. And what our goal is to find the probability that a randomly selected participant achieves a score between Andrew and Chloe's score. So like here, we're trying to find this here, this probability here. Okay, and we can easily do that, of course. So we're basically just trying to find the probability between 117.9 less or equal to x less or equal to 138. And we can use, of course, our CAS here. Let's do that. So let's go in our CAS, go menu, probability, we're dealing with normal here, so normal CDF. So our lower bound in this case is 117.9, and upper bound is 138, and our mean in this case is 120, they told us, and our standard deviation is 15. And you press enter, and this is your probability, so 0.44. Which one looks like that? So it looks like C is the answer. Let me write that nicely. So 5 is C. Beautiful. Next question. Question 6. A biased coin has a probability of 0.4 of showing heads. Remember, a biased coin is an unfair coin. Normally, if it's a unbiased means it's fair. It's going to have 50-50. But this one's an unbiased, so it has a probability of 0.4 of showing heads. The coin is flipped 10 times. Find out the probability of coin showing heads at most. The highest is twice. Is closest to what? A really beautiful question of binomial distribution. So we can say that. So let's represent X as binomial distribution. So X is your the number of basically heads, yep, that you've taken, that you would have took. So that like it shows the number of heads, and out of the 10 tries, so we have 10. So in our how many sample we have 10 with like 10 tries, we're flipping 10 times, and the probability of success of landing a head is 0.4. Absolutely perfect. So we're basically saying, hey, we want to find the probability that the coin showing heads at most twice, yeah? Basically, X has to be less or equal to 2. So, like, at most, it's like the maximum, it's twice, and we can have that 2, basically. Like, yeah. So that's what we mean. The probability of a coin showing heads at most, the most is twice. So yeah, x is less or equal to 2. And we can just do this with our CAS, of course. So let's go do that in our CAS. So we can go to menu, go to probability distribution. Now we're dealing with binomial, but here we're going to use binomial CDF. The number of trials is, of course, 10. The probability of success is 0.4. Your lower bound is, of course, 0. And the upper bound is 2. Okay, and this is your probability. Now it says so the probability of coin showing heads at most is closest to what? So closest to what is 0.17. Like you'd round it up. So because it's actually two answers, like it's saying 0.16 or 0.17. Of course, you got the 7, round it up, 0.17, I would say. Yeah, 0.17. That's the closest. So 6 is D. Beautiful. Yep, because so that's going to be 0.16729, like that, yeah? So, of course, the closest it is, it's rounded up, yeah, 0.17. Okay, perfect. Question 7. Let G be this function where it has this domain, and G of X is this. The range of G is correct to 2 decimal places as well. What a beautiful question that you can do in your CAS. So let's graph this in our CAS, and we're restricting it to that domain. So it's x to the power of 5 minus 3 x to the power of 4 plus 2x to the power of 3 minus 6x plus 2. And of course, restrict it to that domain. So negative 1.1 less or equal to x less or equal to 0. Enter that, and this is how our graph look. Now, so let's look at this really. Let's zoom in. So look at that. Why is it? Yeah, what's that? Okay, so you can see that the range in this case is this value over here all the way to this maximum value, yeah? So just double check it. So this point here is negative 1.1. Now you can see it's actually not 0. The y value is not 0 because you can see how if you zoom in here, be careful guys, do not just assume by looking at the graph. Look, it's not 0. So it has to find that value, of course, we can just easily, we know that the x value here is negative 1.1, which is inclusive. So let me just zoom out. Let's find that y value, by the way. So basically, like, take this graph over here, take this, and basically paste it here, and given, what's the y value? So x equals negative 1.1. The y value is actually negative 0.06. That is the y value here. So you're going from, and that's inclusive, remember? Because negative 1.1 is inclusive. Yep, so you're going from there, so negative 0.06, all the way to this maximum value, and that maximum value is also included, and it's just your maximum value. So press maximum. The y value is 4.71. So basically you're going, and that's also, both are included. So let's go back to our iPad and draw this, just so we can represent it. So I'm going to draw this to actually make it more sense. So for example, this is what the graph looks like. You've got this over here looks like this, like that. Okay, where both of these are included, yeah? We learned that the x value here for this is, of course, negative 1.1, and the x value here is 0. But we know that when we substitute in the y value, this y value here, so the y value of this, so kind of, I'll just represent, so the x value is negative 1.1. The y value was, I'm going to just go back, it was negative 0.06. Let me move this away. Like that, that's the y value. Yep, and the the maximum value here, of course, is now we didn't even need to. We just use our CAS straight away. So from the CAS, we got negative 0.624, 4.71. So you can see that, of course, the range is the lowest value, so negative 0.06, which is included, all the way to 4.71, which looks like B. So these both are included, negative 0.06 to 4.71. So 7 is B. What a beautiful, what an easy question. What a nice question. Next question, question 8. The graph of y equals f of x is shown where f it has a domain of all reals and f of x is this. Okay. The area of the region marked A is the same as the area of the region marked B. Given that A, of course, is greater than 0, find the value of A. What an absolute nice question. So what we're saying here is this. Let's find the x values first, because we're gonna need to find these x values here. Of course, finding the x value is making f of x equals 0, so x to the power 3 minus x equals 0. You have a common factor of x, so it'll be x squared minus 1 equals 0. And of course, you can expand that. Difference of perfect squared. And so you get x equals 0, x equals 1, and negative 1. Now, of course, so this x value is 0. because that's 1, and we don't care about that negative 1. It's very far at the end. So if we're basically saying, hey, we're saying that the area of A is equal to the area of B. That's what they're saying, because it's the same area. That's what they say. The area of the region marked A is the same as the area of marked B. Okay, so basically what we're saying is let's find the area of the area of A first. Now, first of all, it's below the x-axis. So remember, area is positive. So we have to put a negative in front of it to make sure it becomes positive, because area is always positive. And you're going from 0 to 1. You have 0 to 1 of f of x dx. By the way, so this here represents, this whole thing here represents the area A. And of course, it's going to be equal, because remember they said that it's the same. This one's above the x-axis, so it's already going to be positive. We're going for, it's 1 to A of f of x dx. And this is your B. And beautiful, we can just put this in our CAS and it will solve it for us. So first, let's go to our CAS and define f of x. So I'm going to control N this whole thing here. So f of x. Oh no, what happened? Yep, f of x. So it'll be x to the power of 3. What's happening? Yeah, x to the power 3 minus x. Okay, perfect. So we said that the negative integral, oh my god, what's happened? Negative integral 0 to 1 of f of x dx is going to be equal to, I'm just going to copy basically this, the integral from 1 to A f of x dx. Beautiful. And I press enter and I can solve this, answer comma A. And we get, of course, 3 values of A. We remember A has to be greater than 0. So it's not this, of course, because, you know, that's 0. It has to be greater than 0, and this is negative. So it's only A equals root 2. So what an absolutely beautiful question. Let's go with that. Which one's that? It's a C as your answer for that one. Write that nice, so nice. Okay, beautiful. Next question. Question 9. Given that the graph of g of x has a local minimum at 2, 1, the graph of g of negative 2x must be what? This is beautiful. This is actually really nice, because this is, a typical question you can get. Let's draw a graph, and this is just transformations. So if you know your transformations, this is an easy question. Let's look at this. Break it apart. So basically they're telling you, hey, you have a minimum, so at like 1, so that's 2, and that's 1. So this is a minimum value. Say you have this minimum value like that. It's not the most best graph, but say this is your, ew, why does it look so ugly? It's like that. So you say it looks like that, yeah? So this has a, what's your value here? This is 2, 1. So this is how you started. This is your g of x, yeah? This is your original. It has a local minimum at 2, 1. Now, let's look at what transformations have happened. First, looking at this, you have a reflection. Let me write that down. A reflection along the y-axis. The y-axis. That's what's happened. So imagine you reflect this along the y-axis. Of course, it's going to look something like this. It's not the most nicest, but imagine you just reflect it. So what's going to be when you reflect something along the y-axis, you can see that the x values only change. So, for example, this will be negative 2, 1. So the y value is the same. It's still a local minimum. That's still good. Beautiful. That's what's happened. So this here is called g of negative x. So this is how you represent a reflection in the y-axis. And then this over here, this 2 is called a dilation by a factor of half parallel to the x-axis. So you can write that as, so let me write that. So the next one, let me write it. So dilation by a factor of half parallel to the x-axis. Yep. So x-axis, or you can say from the y-axis. Both matter, doesn't matter. But I like to write parallel because it makes so much sense than the other one. Like, for example, what this means is that basically 1/2, like half, is being multiplied by all the x values. For example, so basically all the x values are getting multiplied by a half. So you know how this is our x value over here? This x value for this here is negative 2. It will be multiplied by a half, which basically becomes negative 1. Isn't that correct? And guess what? This here now, you know, it would have, of course, done something, but now this is your g of negative 2x. So this only, do you know what it does? It just basically, all the x values get multiplied by a half, yeah? And so, yeah, like for example, our minimum turning point here would just become, it was -2, just multiply by half, it's -1. Really no difference. So it's still a minimum turning point, and now this is your new coordinate of that turning point for all these transformations, -1, 1, which is basically A. But look, it's still a local, look, so it's still a local minimum, and that's the coordinates, 9A. Beautiful. Okay, next question. Let f of x be this function here, and let g of x be this function, and the h of x is basically g of f of x, then find h dash of x. Okay, not too bad. So, for example, for a composite function, remember to derive a composite function is basically using the chain rule. So, for example, this here, so, for example, we can use the fast chain rule here. So, h dash, I mean, you can use the normal chain rule, but just use the fast chain rule. So, like h dash of x is what? So, remember? You derive the inner function, so it'll be f dash of x, derive the outer function, g dash, and rewrite the function inside. So like this. This is basically the derivative of h dash of x, yeah? If you're wondering, of course you can use the normal chain rule. If you're wondering, I'll also show you the chain rule. Remember the chain rule, what you're going to do is, for those who don't are struggling with this, so you can let u, remember u is always the inner function. So of course that's the f of x, yeah? So it's the inside function. And so we can write now y, this whole function, as y equals g of u. And then you remember you derive both of them. So you derive this, it will be f dash of x, and you derive y, which is just g dash of u. And remember, you multiply these two derivatives and you get the derivative. So it'll be f dash of x times g dash of u. And remember, u, sub back, remember u was f of x, so subbing f of x back in there. And this is your derivative. So that's using their chain rule. And it's the same thing here. Look, that's just a quick chain rule. Okay, we've got that, yeah? Now, what they told us is, yep, okay, but it doesn't look like the answers. Oh my God. So they most of them are written in terms of f of x. So, okay, so what I'm going to do is this. I'm going to derive. So you know how f of x is this? So let me write it. F of x is e2x plus 3. I'm going to derive it, f dash of x. But you remember how to derive it in exponential. You derive the top, which is just 2, and rewrite it. So that's what it is. So so I can write now h dash of x in terms of these. So h dash of x is f dash of x, which is this here. So I can write that there. Times, times g dash of f of x. So first we also need to find the derivative. Let me move this down. We also need to find the derivative of the function g. So what's g dash of x? It's really easy because it's just a quadratic, so it'll be 2x plus 2. And imagine subbing in f of x inside of it. So it'll be 2. Our f of x is what? Our f of x is e 2x plus 3. And don't forget that plus 2. Done. And so we can write it inside here. So that's your g dash of f of x. So it'll be 2e 2x plus 3 plus 2. Done. And you can see you can take a common factor of 2 out. So it'll be 4e 2x plus 3 e 2x plus 3 plus 1. And look, okay, beautiful. And we know that f of x is e2x plus 3, and you can write all this, so it'll be 4. You know how e2x plus 3 is just basically the same as f of x, so we can write it as f of x times, and this is also f of x, remember, because e to the 2x plus, yep, it's f of x plus 1. So this is your h dash of x. There it is. You can represent in terms of f of x. And I think that's what they really wanted to do. So for f of x plus 1, beautiful. So it's 10a in this case. Okay, I hope that makes sense. Next question, question 11. Consider the functions. So f has a domain of 0 to infinity, and f of x log ex. Okay, that's just the maximal domain. And g has a domain of all reals and sine of x. Okay, that's also the maximal domain of just a normal sine function. The range of this function, or this composite function of f g of x is what? This is actually too easy. Because they're all, in the maximal domain, you can just graph this. You can graph f g of x and just look at the range of it. And that's going to be your solution. Now, I'm going to show you that's the quick way. And of course, you want to do the quick way. Do not use the, but I also want to show it conceptually how you would approach it using it by hand. So doing it by hand, because it's important to also know how to do it by hand, because it will develop your skill, especially in the exam 1. So how would you approach this? Well, for example, we know that, I'll show you both ways, of course, but I'm going to show you the actual way that you would approach it. So first of all, for a composite function to exist, we know that the range of the inner function, so g of x in this case, g, must be a subset of the domain of f. Isn't that correct? So what's the range of g? Well, as you can see, of course, the range, to find the range of a sine function, just like a sine or cos, remember it's going to be 2 minus your amplitude and 2 plus the amplitude. So look, 2 minus 1 and 2 plus 1, which is basically going to be 1, 3. That is your range. It must be a subset of the domain of f, and the domain of f is 0 to infinity. And as you can see, it is an actual subset. 1, 3 goes into 0 to infinity. It does work. So this is already the first step, just double checking that this composite function actually does exist. Okay, we got that. Beautiful, beautiful. Now, we can actually, this function exists, I can actually write it down. I want to look at the function. So f of g of x is, so f of x is your log, and g of x is subbed inside the x value. So it'll be sine x plus 2. Beautiful. What I like to first do is draw the sine function first. This inside function, yeah? You're subbing in this inside function. Let's graph what a sine graph will look like. So imagine this is your sine function. So it looked like, it start off, so for example, it will have, so like that's, let's say that's 1, that's 2, that's 3. Starts at, at 2, and it's going to look like this. So, oh my god, it's so ugly. Ugh. Why is this such a pain? Let me draw these lines here. These lines are just going to help me out draw that nicely, especially with that in that range, like that. Okay, so it's going to look like this, like this. Okay, so that's 1 period. Draw another period. Yeah, you can draw unlimited period. It doesn't really matter. So let's just draw 3 periods of it, and we can rub that out. See? And so here it is. So, and of course, 1 period. So this is, of course, just normal period of, it's going to be just 2 pi. This is, of course, 4 pi. 6 pi. Yeah? And the so that's 1 and that's 3. These are your range, or the amplitude for so these. So we need to, okay, so you've got these, yeah? Remember what this is you've got this function, but this is the y value of it. Like, how you've got, so we've drawn sine x plus 2, yeah? Basically this, it's the y values that are being subbed into log e of x, yeah? Does that make sense? So for example, imagine that this here, this function is called y. Look, we've drawn y equals sine x plus 2, yeah? Isn't that correct? To think about, like, sine x plus 2, yeah? Now we're trying to graph what is log e of sine x plus 2. Remember, sine x plus 2 is just y. It's basically what we're graphing is, all the y values of your sine x plus 2 is basically all being logged. All logged. And so that's our graph of a log function. Does that make sense? So, for example, well, we know that, like, these are all where for point the y values are 1. So imagine what's log of 1. We know that log of 1 is 0. So these here in our graph of this here is going to be all in the x values. These are going to be our x, they're going to be actually in the x, here in these x values over here. What about 3? So you know how the y value here is 3? What's log 3? I don't know, but I know for a fact. Wait, let me check what log 3 is. So natural log of 3 is. It's 1.09, so it's above 1. So we can say, like, here, so in these, how it's log e3, it'll be somewhere around here. So all in these maximum here, it's going to look like, and it's just going to have this shape, basically. Beautiful. And log, these are where the y values are log e2, like basically log e2. So what's ln2? Sorry, ln2. It's 0.65, so it's basically like halfway, we can say. Something like that. Something like that. So you can kind of really look at the graph, and it looks like this. Look, putting those points together, you got this nice graph that looks like this. So that graph here, the green one is actually your log function, your log e sine x plus 2. Now, what's the range of it? Well, we know the range, as we can see, is 0, because that's the lowest value where it's included, 0, to the maximum point. And that maximum point is, remember, the maximum for the sine function was 3, and these maximum points are what? It was log e of 3. So when we subbed in the maximum values into the log, it would be log e of 3. So log e of 3. And remember, those are also included. So this here is your range for this function. So 0 to log e of 3, which is looks like would be C as your answer. Now, of course, this is like a long method, and it's important to know how to do this skill. So first of all, let's do it in our CAS, how you would do this in 1 second. Of course, just write it in our CAS, because they're all up to the maximum domain. So, for example, we want fg of x, so ln means just log e, basically. So like log e of sine x plus 2. Enter, and this is it. Look, you can see that it's going from 0 inclusive all the way to the maximum value. It's not 1, because if we go to maximum, it's 1.1, which is basically log e3. Yep, so log e3. Remember when we subbed in log e3, it's like basically 1.1. So yeah, easy. So that's question 11. Next question, question 12. A game consists of rolling a fair six-sided die. So it's a fair. Points are scored according to the following table. So basically, for example, what we're saying is like if you roll a number 1, you get 6 points. If you roll number 2, you get 6 points again. If you roll a number 3 or 4 or 5, you get -3 points. So that's a problem. And if you for example, you roll a 6, you get actual 9 points. So beautiful. Let x be a random x variable representing that the number of points scored per roll. So how many number points? What's the mean of it? Okay, this is actually not too bad. Because what we can do is we can put it in like a probability table, like this whole thing. So let's do that to make it more sense, like make it easier for us. Let's put it in like this nice probability table, where, for example, we have, I don't know if that's like the most, that, like that. So this is where our, okay, so for example, say here, this is our x value. So our x value is the number of points. So for example, so I like to start with the negatives first, like the lowest. So -3. To get -3 points, we can get 6 points or we can get 9 points. Yeah. And this is our probability. What's the probability getting x equals x? So what's the probability of getting a -3? Now think about it. When you throw a dice, yeah, you have 6 sides. Yeah. So what happens when let's look at when you're rolling a -3, yeah? When you're rolling a -3, what's the probability? Well, look, 3 of the numbers, you know how there's 6 numbers? There's 1, 2, and 3. The 3 of the numbers are basically going to give you -3. So it's actually 3 out of the 6 total. You know how 6 is the number of faces? So 3 numbers out of the 6 are going to give you -3. So that's the probability. 3 out of 6. Beautiful. What about 6, the point 6? It's only 2, so 2 out of 6. And 9 is just 1. 1 out of 6. And of course, to add them up, they must equal to 1. And easy, we've got those. And now to find the expected value, it's really easy. When you have a probability table, you can easily find the expected value. But remember, you multiply the x values with the probability. So like -3 times 3 over 6 plus 6 times 2 over 6 plus 9 times the probability. So they're appropriate probabilities. Let's do that. Example. So your expected value of x is going to be, of course, -3 times 3 over 6 plus 6 times 2 over 6 plus 9 times 1 over 6. And so let's put this in our calculator. So we're saying -3 times 3 over 6 plus 6 times 2 over 6 plus 9 times, oopsie, 9 times, what's happened there? 9 times 1 over 6. You press enter and it's 2. So that is your answer. That's your expected value, which in this case is 12 is A. So basically means like when you like rolling, if you roll the 6-sided dice many times you won, the mean, the average of all those points when they, you will get 2 basically, around 2. Beautiful. So 12 is, in that case, it's 12A. Beautiful. Next question, question 13. Let f of x be this function where x has this domain, so 0 to 1 over 2. The inverse of f is, okay, this is such a beautiful, easy question. You can do this with a CAS in 1 second. Of course, do that in real life, but of course, let's also do it by hand, how to approach it. So, for example, we've got the f of x and you've got the domain for it. So, to find the inverse, of course, to find the inverse, what we just have to do is we let f of x by, and we swap x and y, yeah? Remember, we do that. So it'll be x equals e2y plus 4. So it'll be log ex 2y plus 4 log ex minus 4 over 2. And so that's your inverse. So, and which you can write as basically so f inverse is going to be this whole thing here. Now, of course, you can kind of simplify it. You can write it as half log e of x minus 2. And which one's that? That's your inverse. So it looks like A could be that one. B is wrong. And this is C is also wrong. It has -4. So it's a D or A. Now, of course, the difference is their domains. And it's easy. Remember, so we're given the domain of the original function. And so if, you know, for example, to find the domain of your inverse, that's our goal, yeah? The domain of the inverse. These are your domain of the inverse. Is, you remember, it's equal to the range of the original function. So if we draw this original function to this domain, yeah, we can just find the range, and that's going to be our domain. So that's what I'm going to do here. So let's draw axis here. Okay. And so you've got an exponential that has a asymptote y equals 0, of course. This is going to be looking like this. So y equals 0, and it's just going to be rising like that. That's how the graph looks like. And so imagine you're restricting it from 0 to 1/2. So open circle here at 0. Imagine 1/2 is here. And let's rub most of this stuff out. So it looks like this. So the x value here is 0. That is half. Easy? So you can see that the range of it is this value over here all the way to this value, open circles, yeah? What is the y value, though, when you sub in 0 into the original function? So if you sub in 0, it'll be e to the power 4. So the y value here is e to the power 4. What's the value when you sub in a half? So half times 2 is just 1. It'll be e to the power 5. As you can see, so basically it's your range is going to be, you know, so you remember the range of f is what? It's basically open circle e to the power of 4, so all the way to e to the power 5. And remember, that's the same as the domain of the inverse. So which one's that? It's D as your answer, Rook. D actually has that over there. Whereas this one's 0 to infinity. Beautiful. Really, really nice question. Again, let's do this by CAS. How would you do this, CAS? First of all, I will define it. I'll define this, you know, function. So straight away, 2x plus 4. And I'm going to basically define the rule for the inverse. I'm just going to solve. All right, so solve f of y equals x comma y. And so this here is my inverse. This is my inverse. So for example, this is my inverse equation, which is the same as what we got, yeah? And to find the domain, we just have to actually sketch this original function f of x, yeah? So imagine just sketching. What did I do there? So sketching f of x, of course, from that domain. From that domain 0 to, so the 0, that's equal to x, that's equal to basically half. There it is. Which, what the hell did it speak for? Don't know what just happened, but no stress. Got you. So we got this from 0, that's equal to x, that's equal to a half. Yeah, damn. How's it? Is it not? It's drawn, but am I not seeing it? So menu, maybe zoom fit it. Yeah, it is drawn. What the hell? Yeah, but yeah, it makes sense. It was drawn, but it's so ugly. But yeah, it looks like this. So from this point all the way to this point, which is e to the power 4 all the way. But it's so ugly. Just drawing it by hand would be much more beneficial. Yeah. So question 13 is D. Let's go to the next question. 14. 14. Consider the functions of f of x as that and g of x as that. Get each defined over its maximal domain. The maximal domain of the product function h of x, f of x times g of x is what? What an absolute perfect question. I think this question actually came up. There was a similar question like this in the 2024 real exam. So like the normal exam in November that's taken. Yeah, a really easy question. Now remember, for sums, if you have two functions, so if you, like for example, if you have two functions added, minus, multiplied, to find the domain, of the overall function, so like for example h of x, it's basically finding the domain of each of them individually and finding that point of intersection, and that's going to give you the domain of h in this case. So yeah, and that works for both two functions adding, minusing, and multiplying. So for example, this is a product function, so they're being multiplied. So remember what we said. If we want to find the domain of h, in this case, we want to find the domain of h, is going to be basically equal to finding the domain of f intersecting the domain of g, which is really easy. So for example, your CAS can do this in 1 second. I'm not gonna lie. We're gonna also do it by CAS, of course, like just in 1 second. But I just want to show you how you would do it by hand, because this is like it's like a typical exam 1 style also. So for example, domain of f is what? So the domain of f is, you have this log. Remember, to find the domain for a log, it's just basically taking the inside and solving it where it is. So it's taking the inside here and it's solving it where it's greater than 0. Of course, factorize this. So if you factorize that, what's that going to be? 3, 1, 3 negative. Yep. So it'll be basically, if you factorize, it'll be x plus 3. X minus 1 is greater than 0. So if you graph this here, so imagine making 2 graphs. So you've got this graph here, the red one, and this is the yellow one. So the y equals 0. So you're solving this inequality, remember? So let's draw the parabola, which is our red graph. So negative 3 is here, 1 is here. Just a normal graph that looks like this. Yeah, come on. Why is it not drawing me this parabola nicely? Why? I'm actually like, who cares? Come on, I really want to draw this parabola nicely though. Yeah, why? Why is this? No, it's actually taking a piss out of me. I swear. Yeah, I'm not doing that. I couldn't care less. Okay, we got this here. Okay, we got this. Okay, so we've got this parabola here. That's from negative 3, 1. We're basically saying, and let's also draw the y equals 0 line here, with the yellow line here. We're basically saying, hey, when is the red line greater, so bigger than the orange line? Well, we can see it's from here and here, which is basically what I do. X values, of course, your x value, that's your going to be your domain for this f of x. So your domain, let me write that nicely. The domain for this f of x is basically going to be from negative infinity to negative 3 non-inclusive. Remember, it's non-inclusive, it's greater than 0, union 1 to infinity. And so we can write that there. So the domain of f is negative infinity, negative 3, union 1 to infinity. So that's your domain of f. Yeah, so I'm just going to write that there. Who cares? Like, yeah, just that's your domain of f. How do you find the domain of g? G is so easy because it's a square root function. To find the domain for any square root function, you just make the inside function, so that 2x plus 7 to be greater or equal to 0, which is 2x greater or equal to negative 7, and hence x is greater or equal to negative 7 over 2, which, so your domain, alright, so domain of g is negative 7 over 2 to infinity. Okay, which now you can put these together. So to find the intersection between these two domains, of course, just draw a basic number line, and you can easily find those out. For example, negative 7 over 2 is here. So negative 3 is over here. 1 is here. So for example, let's make this, of course, red. Let's make this red, for example. And let's draw this domain first. So negative 3, non-inclusive to, like negative infinity to that, so like that. And 1 to infinity. So non-inclusive 1 goes to infinity, positive infinity. Let's make this here as yellow. For example, this here is yellow. So you're going to negative 7 over 2, so inclusive though, all the way to infinity, positive infinity. Done. So what is the point of intersection in this case? Your point of intersection is, as you can see, it's here and here, which is what? So it'll be x is an element of what? So it'll be, negative 7 over 2 inclusive, because there's inclusive there, to negative 3 non-inclusive, union 1 non-inclusive to infinity, because it goes forever. That is your domain, which looks like D. That one is D. And that's how you do it by hand. Now, you're not doing this, of course, but to do it, of course, by CAS, let's do it. So just go in your CAS, of course, and just write domain domain, you want to find the domain of f of x. So f of x is your log function, so log e, x squared plus 2x minus 3 times by g of x, which is 2x plus 7. And don't forget comma x. There it is. So the same thing. Look, -7 to inclusive, to -3 non-inclusive, and 1 to infinity, where 1's not included. What an absolute easy question. So a really typical, beautiful question. Okay, question 15. The function g is differentiable over the domain R. Okay, beautiful. And satisfies that g of 2 equals g of 4 equals a, and g dash of 2 and g dash of 4 equals b. Given that p of x is this function, so we've got two functions being multiplied, then p dash of 2 must be what? This doesn't look too bad. I've seen this actually quite a lot in the Kiel-Baha papers, so it's not too bad. So it's like a typical beautiful question. So, for example, we want to first find the derivative of, if we want to find p dash of 2, we need to first find the derivative of p of x. And so, first of all, to find the derivative of p of x, we have two functions being multiplied. Of course, what rule should we use to find the derivative of two functions being multiplied? The product rule. So let's make this u, of course, and let's make this v. So our u in this case is g of x, and our v in this case is g of 2 of x. Of course, your u dash is g dash of x, and your v dash, remember, is basically just using the quick chain rule, derive the inside, which is just 2, derive the outside, which is g dash, and rewrite it 2x. Beautiful. And of course, so hence your p dash of x when deriving p of x is basically, remember, it's u times v dash, these two multiplied, so it'll be 2 g of x, g dash of 2x, plus these two multiplied, g 2x times g dash of x. That is your derivative. And of course, you're basically just subbing in 2 into it. So p dash of 2, so for all the x values, you're subbing in 2. So it'll be 4 here, will be 4 dash of 2, which is equal to what? So what's first? G of 2. Now we know what g of 2 is. G of 2 is equal to a. So we can put a in here. Times g dash of 4. What's g dash of 4? We know that g dash of 4 is equal to b. So we can put b in here. Plus g of 4 is g of 4 again is a. Times by g dash of 2, and g dash of 2 is equal to b. Adding those up, it is 3ab. That is your answer, 3ab, which in this case is 15c. What a beautiful question. Nice. Next question. Let x be a normal random variable that satisfies that the probability that x is greater than 6 equals the probability that x is less than 8, which is equal to the probability that z is less or than 0.5, where z is just basically, of course, the normal, the normal distribution, which is the standard normal random variable. Let the standard deviation of x as well. So first, there's so much input happening. There's so much information. What I first like to do when I see these kind of questions is to first draw a nice diagram to represent this whole thing. So let's draw a normal diagram. Like a really nice normal diagram. Okay, like that. So this is your x, like that. Okay. So so what they're saying is the probability that x is greater than 6. So let's say 6 is here. Let's say 6 is here, yeah? So imagine that point here. So the probability, all this here, is going to be this probability here. So imagine all this probability here is equal to the probability that x is less than 8. So wait. So around here, 8, this here, this probability here, and these probability have to be equal. These two are equidistant because look at this. If you, for example, what they're saying is, hey, the probability that x is greater than 6, so all this probability here, all this area over here, is equal to the probability that x is less than 8, so all this probability over here. You see that? So these here are equidistant. They are basically equidistant, basically. This is actually perfect. If they're equidistant, you know what that means? Remember, if you have two things that are equidistant, you can average them out to find the mean. So we know that the mean has to occur in that middle, yeah? So just average 6 and 2. So it's the midpoint between these two. So if you find the midpoint, it's just basically adding these two values up, which is 14, and divided by 2 is 7. So midpoint is actually 7. That is your mean. Think about it. That's your mean. Yeah? Okay. So we got the mean now. Yeah? This is actually good. They also tell us that the probability that z is less than 0.5 is equal to that probability. Now, if you kind of think about it, think about it like this. So imagine your z is here. Yep. So basically they're saying probably that z is less than 0. But it's basically z has to be here, by the way. So you know that mean is 0. This z has to be 0.5 here because remember it's equal. So you know this probability here, saying it's saying probably that z is less than 0.5. It's equal to the probability that x is less than 8. So basically that 0.5 is basically equivalent to that 8 in terms of x. And so so if we use like the normal if we convert this x into z, so for example, probability that you know how x is less than 8, let's convert it into z. It'll be, you know, you would say z is less than, of course you say 8, minus your mean, we know our mean is 7, over your standard deviation, which we don't know. And that's going to be equal to what? So it'll be z is less than 1 over your mean. Now, this here, it's equal to 0.5, yeah? Remember, that's equal to 0.5. It's the same, yeah? So look, we're converting 8 into that. It's, you know, equal to 0.5. So 1 over your standard deviation is equal to half, basically. 0.5 is half. So your standard deviation is basically 2. What an absolute beautiful question. So critical thinking here. What a nice. So question 16 is C. Beautiful. Question 17. In a set of 10 products, 6 products are defective. 2 products are randomly selected without place. Oh, yeah. I hate without replacement. So 2 products are randomly selected without replacement. From a set of 10 products, it is known that at most one of the 2 products are defective. So why would they give you this extra information? They're giving you here. It's a given question. Do you see this extra information they've given you here? Why'd they bring it here? It's because it's given. We're probably going to be doing with conditional probability here. So what is the probability that exactly one of these 2 selected products is defective? So what I'm going to do is, when you're dealing with non-plus, I like to kind of explain it using a tree diagram. It just makes it so much easier to understand. So what I'm going to do is I'm going to draw a nice tree diagram. So of course, we're taking, how many products? We're taking 2 products randomly, yeah? So imagine this is your first product, so because you can get a defective and non-defective. And the same thing, so I might as well just copy this actually. Duplicate it there, duplicate it there. Like that. Well, of course, you can get defective, non-defective, defective, non-defective, and that's your second product, yeah? Now, they told us that the probability, so in a set of 10 products, 6 products are defective. So defective probability is 6 out of 10. Yeah, 6 out of 10. So this has to be 4 out of 10. Now, of course, remember, it's replacement. So without replacement. So this will be, of course, you minus 1 here and you minus 1 here. So it'll be 5 out of 9. And you do the same here. So you minus 1 from the top, minus 10 from the top. That's the quick way. 3 over 9. And so remember, these have to add up to 1. So this will be 6 over 9. Ugh, come on. 6 over 9, and this here would be 4 over 9. There it is. That's the add up to 9. Yeah, beautiful. We got all those up. Now, we need to write this here. So it is, what is the probability that exactly, so we're finding, what's the probability that exactly one of the 2 selected products is defective? So let's call D, so we want exactly one defective, yeah? But remember, this is like they've given you this extra information. This is conditional probability. It's like, so imagine given this information, find the probability of that. So you're going to have to put given, it is known that at most, so the maximum that you can have is one of the 2 selected products. Basically, D has to be less or equal to 1. So you want to, like, does that make sense? So at most you can have is 1 out of those 2 to be defective. Okay, and of course you need to find the, remember your conditional probability formula is to find the intersection between these 2. And to do that, you can just kind of draw a number, easy number line for those who struggle. So imagine that's 1. So you have 1 here, which is inclusive, so just D equals 1. And D is less or equal to 1. So it's just this and less or equal. So where is the point of intersection? It's just this here, D equals 1. So you can, it's just equal to the probability that D equals 1 over, remember, using the conditional form, the right one. So probability of D is less or equal to 1. So that is what we need to calculate. Which is not bad, because we got most of the information from this. We can get most of this information from this tree diagram. So let's do that. Okay. First of all, we need to find the probability that D equals 1. We only want 1 defective. Well, that's kind of easy because, look, for 1 defective, you can have this possibility here. So D dash. So the first one's defective and the other one's not defective. Whereas you can have, like, and then you have also this possibility where the first one's defective and then next one is actually, no, wait, what am I saying? So where the first one's not defective and the other one's defective. So you got these 2 possibilities here. Does that make sense, everyone? So let's find these probabilities. So of course you have to add them up. So first of all, to find this first one, it's going to, so first, of course, this one over here, it's just 610 times 4/9 plus that. The next one is 4/10 times 6/9. That's it. So that's d equals 1. What about the next one? D is less or equal to 1. You can write that as just basically d equals 0 and d equals probably that d equals 0 plus the probability that d equals 1. You can write it like that. So where you can have like 0 or 1. So 0 defective plus the probability that d equals 1. So 1 defective. Now, and what is that? So for 0 defective, it's these ones here. And plus with 1 defective, remember it's these two here. So it was this one and this one. So wait. So it's basically everything except that both defective here. These two both defective. Why don't we make our life easier? Is to find both defective and 1 minus it. So 1 minus these both defective ones, yeah? Because that's 2 defectives, yeah? 1 minus, and it will give us the rest of the whole probability. You know how we have to do all these probabilities too much. So why don't we just do 1 minus 6/10 times 5/9. And that's it. So let's put this in our calculator and hopefully it gives us a nice answer. Okay. So it will be 610 times 4/9 plus copy that. So 410 times 6/9. Then 610 times 5/9, which is 4/5, which looks like A is your answer. So 17 is A. Beautiful. Next question. Question 6 is algorithms. Consider the algorithm below, which can be used to find the approximate solution to this equation. Log EX minus x/3 equals 0. Okay, beautiful. So basically it's saying, hey, define f of x, so defining f of x, and they return this value, which is this function here. So basically they've just basically defined, so f of x is defined now. Your f of x function is basically equal to how you define normally your cas. You know how you define a function? It'll be log x minus x/3. That's what they've defined this function to be. Now, what they're saying is a equals 4. So let's also write everything down when you're doing these types of questions. So a equals 4. B equals 6. And so for I from 1 to 3, so I means iteration. So I equals 1. So I'm starting with 1, then I reiterate it to 2, then 3. So that's how what iterations means. So for I from 1 to 3. So of course we're going to start with the first I, number 1. C is going to be equal to A plus B divided by 2. So imagine adding these two up. 4 plus 6, which is 10, divided by 2, it's 5. So C is actually equal to 5. And so let's check if this if works. If f of c, so we can just do that in our calc, is f of c between negative 0.1 less, so f of c between negative 0.01 and 0.01, well, we can just double check that with our calculator. Come on, so easy. So control N this, and let's actually define this in our cas. fx, let's define the function first, which is, what am I doing? Log e x minus x/3. Okay, so first of all, what I'm doing is we're basically saying, hey, is negative 0. I'm going to write that. So is negative 0.01 less than x f of c. What's our c value? Remember, c value is 5. So f of 5 less than 0.01. 0.01. It's a false statement. Your actual f of I is not between it. So we actually have to skip that step. Look, do you know how it says if negative 0.01 is less than, so this here is, it doesn't fit. So we can't actually move on to printing it. We have to move on to the next thing, which is else if. So we need to check the next one. It's saying else if f of A times f of C is less than 0, then, okay, let's double check that first. So going back, so first f of A, so f, what's our A value? Of course, 4 times f of B, which is 6, and enter it, control enter, which is this. So basically saying is f of A times f of C less than 0. It is. You can see it's negative. I mean, you can just take this actually and just say, is that, less than 0? It's true, yeah. It is less than 0. So we can actually do this statement here. We can update that B equals C now. So your B value becomes C. So this here will become 5. Okay, done. And so that is it. And of course, skip this one. Why do we look? So this one worked. So we can actually, and we don't do this one. Remember, we don't do this one because, remember, only if this failed, we have to move through this one. So we can actually move to the end if now. Okay. Now, we come back we come back to the second iteration, yeah? Because we're not printing, look, the question says, which of the following numbers would be printed by this algorithm? We need to find which one will be printed. So that's the goal. And you can see we haven't printed anything still. So we need to go back to the second iteration. So imagine repeating this whole thing and then put now 2 here, your second iteration. So repeating it. Now C is going to be equal to A plus B divided by 2. So 5 plus 4, which is 9, divided by 2 is 9 over 2. So that's your new, so 9 over 2, which is 4.5, 9 over 2. Yep, easy. That's your new C value. So now let's check if this statement works. So coming back here, just kind of copy this and put 4.5 here. Does that work? It does work. So now if actually this statement here works, when you C value, now we can actually print C. If we print C, this is our solution. That's what's going to be printed out by this algorithm, 4.5. So, oh my God, so C equals 4.5. So it's B. What's that question? So question 18 is B. Beautiful, not too bad. It's a really easy, this one's like the most easy algorithm you can have. It's really nicely written. Next question, question 19. Let B and C be discrete random variables whose values are obtained from 2 rows of a fair six-sided die. Okay. Let B be the number obtained on the first row and let C be the number obtained on the second row. Okay, so any of these numbers, so out of 6. Find the probability that the quadratic equation x squared plus bx plus c equals 0 has at least one real solution. What the hell is this? This is just unique. This question is totally unique. So B here, so remember B and C represent the number obtained from the first row and the second row. So C represents the second row, B is the first row, and they are actual within this quadratic equation. And what we want to find is that we want to find the probability that this quadratic equation has at least one real solution. Okay, so first of all, to find any real solution, we need to first use, of course, the discriminant. So remember your discriminant is, of course, b squared minus 4ac. Isn't that correct? Yeah? Now think about it. We want to find at least one real solution. So, of course, you know, you can have equals 0. Equals 0 is 1. So it basically gives you one solution. Because remember, yeah? And b squared minus 4ac can be greater than 0, which gives you two solutions, which look both fit this condition. Do you see? At least one real solution means that you can have greater or equal. So putting these together, these components together, because they fit both of them, is going to be, it will be this, greater or equal. Basically, we're solving this. This will actually give me, when solving this will give me at least one real solution. This is what we're doing. And so it's subbing, what's our b squared? It's this b, big B. So b squared minus 4. Our a is 1, so just nothing. C is this big C, is greater or equal to 0. All right, so we got this. kind of nicely write it. So bring that to the other side, this 4c here. Okay, we got this nice dimension. So your b squared, so basically b is the number that's obtained on the first row, and c is the number obtained on the second row. And it needs to fit this inequality for it to work, to have one real solution. Now, there's so many combinations. You have 6, like 2 dice, the other one has 6, the other one 6. So one of the best ways that I represent it is just using a normal diagram, like, the diagram to represent all of them. So like for example, this one. So for example, so let's consider this here. So that's 1. That's your die B, by the way. So that's 1. That's 2. You can roll 3, 4, 5, 6. So that's your 6. Let's call this die B. So the top, and this part here. So it's the same thing, like 1. That's your die C in this case. 2, 3, 4, 5, 6. And this here is your die C, your second die. Now we need to check all of that. So you remember, let's check the first value. So when b equals 1, to check this box. So for example, b equals 1 and c equals 1, yeah? Let's check if this inequality works. For example, if I sub in, 1 on the b, so b squared is greater or equal to 4, and our c value is 1. Is 1 greater or equal to 4? Absolutely not, so we can put a cross on that. That doesn't work. And you can just do that. Imagine doing it for all those 36 numbers. That's a lot. well, we can actually make it more simple if you kind of think about it. Well, for example, what we can do is do this. Like, we can just sub in one value. Like, for example, B, yeah? Let's try to sub in B, only B, and solving for C. For example, if I sub in B for the point 1 here, so B1 squared is greater or equal to 4C, and I can solve for C. So B1 is greater or equal to 4C. I can, it becomes 4C, switch them around, is greater or equal to 1. And so here C is greater or equal to 1 over 4, which basically is C is greater than equal to 0.25. So the C values that work for this one is, like, it has to be less or equal to 0.25, which in this case, you have 2, 3. These are all like they don't fit with this domain, so they're all wrong. These are all going to be crosses. These are not going to work with this inequality. So look how quick we can just kind of rule them out. And so imagine doing that for the next one. So again, doing it for the next one, like B equals 2. So putting 2 squared here is greater or equal to 4C, and we solve for C. So 4 is greater or equal to 4C. So 4C is less or equal to 4. C is less or equal to 1. What about C is less or equal to 1? Look, it's equal to 1. So actually 1 works. So we can put a circle here. That it works. But then 2, 3, 4, they're not within this domain. So we can actually have to cross these out. Those won't work with this inequality. So they're not going to give us at least one real solution. And we have to do that for all of them. And this is not too bad. So like, for example, this one here, 3 squared greater or equal to 4C, which is 9 less or equal to 4C. 4C less or equal to 9. C is less or equal to 9 over 4, which is 2.25, I think. Yeah. Yep, that works, 2.25. So you can have 2, 1. So 2 and 1 work within this one, yeah? So the C values for 2 and 1. So look, 2 and 1, but the other ones all don't fit in it. So we can rub those out. And yeah, just like this. This actually just makes it easier doing it like this than subbing it individually. You'll take so long. So for example, the next one's 4. So 4 squared is greater or equal to 4C, which is of course 16 greater or equal to 4C. So 4C is less or equal to 16. C is less or equal to 4. So this one actually 4, 3, 2, 1 all fit into. So 4. So basically all of these. So yeah, and these are all going to be crossed out. And let's try 5. 5 is just basically going to be 25 less or equal to 4C. 4C is less or equal to 25. C is less or equal to 25 over 4 is what? It's basically like 24 over 4 plus 1 over 4. 6, 4, 18, 24. So it'll be 6, basically 6.25. And that actually works for all of them. Like the C value, like 6, 4, they all work. So these all work. These are within that domain. Okay, let's try the last one. What about 6? So 6 is 36 squared is 36. That's equal to 4C. So 4C is less or equal to 36. C is less or equal to 9. And that also works. All of these works. They're all less or equal to 9. Okay, so the circle ones are the values for both B and C where we will have at least one real solution. So counting them in total is how many? Out of the total, the total is 36, yeah? And the circle ones are how many? So we have 6, 12. So for example, 12 in these first ones. So 12, adding these up, 12. 12 plus 4, that'll be 4, 6, 1. So 7? Yeah, 7. Which is 19 over 36. 19 over 36 is 8. That is too unique. That's a really unique question. I've never seen that question before. So it's a really unique kind of question that's just ugly, to be honest, but very unique. 20. In the xy plane, so just in the x and y plane, there's a system of 2 linear equations with a unique solution, and another system of 2 linear equations with an infinitely many solution. These 4 linear equations are combined into a new system of 4 linear equations. All possibilities for the number of solutions of this new system will be what? Okay, what are basically the solutions? Okay, so let's think about it. So for normally like a systems of equations, yeah, let's just think about it basically. For normally a system of equations, like 2 systems of equations, we know that for a fact that when we're solving 2 systems, like a system of equations, imagine you have 2 equations. When you're solving it, it's the point of intersection between the 2 lines, yeah? That's the solutions. So for example, if you have 3 equations, it's basically, for example, when you have three of these equations intersecting all together. You see these? That's one solution, because that's where they all intersect. It has to be all those lines intersecting. All of them have to be intersecting. For example, you cannot just have these two intersecting and this one over here. Then that's no solution, because look, these two are intersecting. What about this one? This has to also, for solutions, they all have to intersect, yeah? All of them have to intersect a point. So that's what we have solutions. So just remember that, yeah? Okay. Now, so for example, let's say that so there's a system of equation where two equations have a unique solution. Remember, unique solutions when you have two lines that don't have the same gradient, like this. So let's draw them all in different colors. So imagine you have this here over here, this color here, and you have another one, this red line here, which is this here. Do you see how the gradients are different? Can you see how they have unique means just one solution? Look, just one solution. So imagine those are the two first equation. But then they told you that the other two linear equations are infinite linear solutions. Remember, infinite linear solutions, when they are on top of each other, basically they're the same equation. So let's draw like another equation. Let's say like this. So imagine, actually, this, I don't know. Let's just say something. I'm thinking of like what kind of, because I don't want to make it. Let's say, yeah, you got this equation here, like that, and then another equation. Remember, they're going to be this kind of the same. So, like, imagine what's on top of it. I'm not going to really draw on top, but like that. I'm going to draw it like that. So imagine that on top of each other, yeah. And so these are all equations. Isn't that all our equations, basically? Yeah, they are. These are our four. So basically we're saying, hey, imagine taking all these linear equations and just making a whole new system, yeah? And what are the possibilities of the solution of this new system? Remember, because we have four equations now, four linear equations, to find solution means where they will intersect all together. They have to all intersect at that point for it to be known as a solution. So, for example, can you see how here, this is, can you see how these two equations here are intersecting at this point? Well, for example, if we have these ones over, you know how, let me take these out. So you know how this over here, these infinite solution, if they are just put over here, can you see how all the lines, are now intersecting this point? Every line. So all the four lines are intersecting this point. That means that there's a possibility of one solution, because they intersect once. So one is an actual solution. You can actually, so the possibility of number of solutions of this system will be what? So we can already, just by looking at inspection, we know that there's going to be one solution. Oh no, that's bad. They all have one solution. That is 100% an answer. Damn. Dude. Okay, that was bad. So, because that was really easy to look at. Okay, what about the other stuff? Okay, let's look at the other stuff that we can approach this with. I'm going to think about this. Okay, so what about infinitely many solution? Let's say if there's infinite many solutions. For infinite many solutions, all the four lines have to be like on top of each other. Isn't that correct? But that's impossible because, first of all, like one of these can be having the same gradient as that. It worked. But remember, these two are unique solutions. Their gradients are not equal. So for an infinite many solution, all of the lines had to be within, like all of them have to have the same gradient. So for example, if I drew it, imagine all those lines, like 1, 2, 3, 4, they're all on top of each other, yeah? And then that's an infinite many solution. In this case, you can, because, you've got these two which are unique. They don't have the same gradient. So you cannot even reach that. Infinite many solution is impossible. So straight away, anything with infinite, rubbish. Okay, so we have A and C. So one, of course, works, but now we need to look at, is it zero solutions? Of course there's zero solutions. Didn't we just actually prove that too? So for zero solutions, we said that, for example, why did I rub that out? So for example, for zero solutions, this is zero solutions. Like if you just take this line and put it over here, this is zero solution because they don't have any point of intersection. Like for example, how these are intersecting? This is not an actual solution though, because all of the lines have to intersect. Look, these all three lines are intersecting, but still not a solution because all of this one here is not intersecting at that point. Also, for a solution, all those four lines have to be intersecting. Do you see that? Look, that's a possibility. That's called no solution, yeah? Does that make sense? So we can, of course, have zero solutions. That's zero solution because, they're not all intersecting. So you can have 0 and 1, not infinitely. Yeah, infinitely many is rubbish. So, yeah, absolutely. A. I would say A in that case. That's how I would have approached this question. Yeah, and that's it. I hope you guys enjoyed this video. I hope it helped you out, understanding this paper. Not a bad paper, I'm not going to lie. The multiple choice is actually quite nice. Of course, the two last questions were kind of brain rot, to be honest. They kind of destroyed my brain cells. But overall, not a bad paper in terms of the other questions. They were really beautiful. So I hope this video helps you with your studies and good luck. I will try to make exam 2 solutions, but I'm really tired right now, so I'll probably make it tomorrow. All right, guys, have a great day. Bye-bye.